It's been more than 50 years since man walked on the moon for the first time. From one giant leap for mankind to building and launching the International Space Station and other space exploration, scientific advancements have brought us closer to an optimal understanding of the universe. An integral tool for space exploration is the Space Telescope. Over the decades, scientists have pooled their minds and resources together to create some of the most powerful telescopes. The James Webb Telescope is by far the hallmark of intellectual ingenuity and the dedication of these scientists. So you may ask, what sets the James Webb Telescope apart from other kinds of telescopes? Well, stick with us to find out. The purpose of this space telescope is to carry out infrared astronomy. Its high-sensitivity, high-resolution design and makeup enables it to examine objects that the Hubble Space Telescope cannot see because they are too dim, ancient, or far away. Which is why the Webb Telescope has been tagged the successor of the Hubble. Infrared astronomy refers to the study of celestial objects through the use of infrared IR radiation. Since infrared light has a wavelength between 0.75 and 300 micrometers, which lies between visible light and ultraviolet, the telescope is able to capture images much clearer than how they really appear. The best part about the Webb telescope are the possibilities one can expect from the telescope. What do I mean? Well, according to NASA, for the first time ever in human history, the telescope will show the furthest parts of the cosmos, which will allow for studies in a wide range of astronomical and cosmological domains, including the first star observation, the birth of the first galaxies, and the in-depth atmospheric characterization of exoplanets that may be habitable. There is a likelihood that the telescope will be able to confirm or disprove the Big Bang Theory, the controversial but fairly scientific assertion that our whole universe started some 13 billion years ago, and after some time, energy burst out and it began to expand and cool and evolved into what we see today. The telescope is named after James E. Webb, who oversaw the Apollo, Gemini, and Mercury missions while serving as NASA administrator from 1961 to 1968. The telescope was built by a collaboration of government agencies and many bright minds. The European Space Agency, ESA, and the Canadian Space Agency, CSA, were the two main agencies that collaborated with the U.S. National Aeronautics and Space Administration, NASA, to oversee Webb's design and development. But in order to make the telescope's construction easier, these agencies employed Northrop Grumman, a private contractor, to facilitate building the telescope. However, during the launch of the telescope, some 20 countries collaborated and supported this next step of human advancement. There was also a host of academic and private individuals who came together to add finishing touches to the project. All in all, more than 1,200 individuals were involved in building, testing, and launching the telescope. On December 25, 2021, the Webb was launched into space from French Guiana. It reached its programmed destination in January 2022, which was a solar orbit not far from Earth, roughly 1.5 million kilometers, or some 930,000 miles from Earth. Presently, the Webb telescope is run and managed by the Space Telescope Science Institute in Baltimore, located on the Johns Hopkins University campus. But this isn't the first time a telescope would be launched into space. What makes the James Webb Telescope unique? Well, here is what we know presently. Because of its infrared vision, the Webb telescope can function as a potential time machine, allowing us to look back over 13.5 billion years of the existence of our universe to see the formation of the first stars and galaxies at the instant of the Big Bang. The Webb telescope is currently providing us with additional information about the atmospheres of planets outside of our solar system, and may eventually find life somewhere else in the cosmos. The telescope is also examining objects in our own solar system. To understand our universe better and make succinct deductions. Another objective of the telescope is to better comprehend how galaxies assemble over billions of years. Scientists hope that the Webb telescope will enable them to make comparisons between the earliest galaxies from the beginning of the universe and today's vast and gigantic constellations. For a project of this magnitude, take a wild guess of how much it will cost. Have you done that? Well, according to NASA, they estimated that the project would cost the US $9.7 billion in total when it began in 1996. Of that amount, $8.8 billion would go toward designing and developing the spacecraft for carrying the telescope, and $861 million would be used to fund 5 years of mission operations for the telescope. The project contributions from the European Space Agency amounted to about $746 million and $146 million from the Canadian Space Agency. The entire cost of the Webb telescope totaled to a little under $10 billion when it was finally launched at the end of 2021. Now let's talk about how the James Webb Telescope has been dubbed the successor of the Hubble. While many scientists prefer not to make comparisons between both telescopes, without a doubt, the Webb telescope is an improvement on the Hubble, and this is so apparent in so many ways. How so? The Webb telescope features 4 main instruments to take pictures and images of cosmic objects. It observes celestial bodies in infrared. The wavelength range covered by these instruments is 0.6 to 28 micrometers. This indicates that the electromagnetic spectrum's infrared region will be the main operating region for the Webb telescope. On the other hand, the principal capabilities of Hubble are in the ultraviolet and visible regions of the spectrum. While its instruments can detect a small fraction of the infrared spectrum, from 0.8 to 2.5 micrometers, it is unable to function like the Webb telescope. Thus, the Webb telescope can view objects and bodies at a much clearer degree than the Hubble because of its level on the electromagnetic spectrum. The primary mirror on the Webb telescope has a diameter of about 6.5 meters, which gives it a far bigger collecting area than the mirrors on other types of space telescopes, such as the Hubble telescope. Hubble's mirror has a diameter of only 2.4 meters, and its matching collecting area is only 4.5 square meters. To put this into perspective, the Webb telescope has around 6.25 times greater collecting area than other telescopes, including Hubble. Additionally, the Webb telescope's field of view is substantially greater, about 15 times larger than that of the Hubble telescope camera. Just to put the structure of the Webb telescope in proper context, consider the following dimensions. The Webb telescope mirror is composed of 18 hexagonal mirror segments constructed of gold-plated beryllium, totaling a diameter of 6.5 meters, or an impressive 21 feet of reflective surface. This means that Webb's light collecting area is approximately 6 times larger than Hubble's, at about 25 square meters collecting area. Let's consider how both telescopes orbit. The Hubble telescope was intended to orbit the Earth at a height of 515 kilometers, barely above the atmosphere. On the other hand, at approximately 1 million miles from home, the Webb telescope orbits the Sun and Earth around a point in our cosmos called the second Lagrange, or L2 point. Because the Sun, Earth, and Moon appear in the same region of the sky from the Webb telescope's vantage point, its massive sun shield will be able to protect the telescope from direct sunlight, which helps keep the telescope cool. As an added bonus, L2 is a simple location for the telescope to maintain its orbit due to the gravitational pull of the Sun and Earth. The Webb telescope will therefore require few light rocket thrusts at L2 to keep its orbit stable and stay on mission. Another disparity between both telescopes lies in scheduled maintenance. What do I mean? Because Hubble orbits just above Earth's atmosphere, initial plans before launch revealed that there is the possibility of Hubble returning to the planet for repairs and reprogramming as part of their long-term strategy. Because of this possibility, the telescope's design takes into account the size of its launch and maintenance vehicle. However, as far as we know, there is currently no service plan or hands-on maintenance scheduled for the Webb telescope. And the reason for this is not far-fetched. The telescope is more than 1 million miles away from Earth, 4 times further away than the Moon. Therefore, the architecture and design of the telescope was made to be independent of servicing flights or any hands-on maintenance. To conclude, let's consider some of the instruments present of the Webb telescope and how they function. First is the near-infrared camera, or as it is commonly called, the NIRCam. The NIRCam is an infrared imager with substantial coverage that extends from the near-infrared, which is approximately 5 micrometers, to the visible light spectrum's edge, which is approximately 0.6 micrometers. There are roughly 10 4-megapixel sensors on the NIRCam. The NIRCam works as the telescope's wavefront sensor, and it is necessary to sense the wavefront and regulate the telescope's operations. It is also employed in the primary mirror segment's alignment and refocusing. Next up, we have the mid-infrared instrument, and it is used to measure the mid to long infrared wavelength range, which spans from 5 to 27 micrometers. It has an imaging spectrometer and a mid-infrared camera. MIRI was created as a joint project of NASA and many European nations. Another instrument present on the telescope is the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, the FGS NIRIS. When conducting scientific observations, the telescope's line of sight is stabilized by the use of this apparatus. The fine steering mirror for image stabilization is driven by the FGS measurements, which are also used to regulate the telescope's overall orientation. On the other hand, the NIRIS module allows for astronomical imaging and spectroscopy in the 0.8 to 5 micrometer wavelength range. It was contributed to the project by the Canadian Space Agency. Despite the fact that they are sometimes referred to as a single entity, the NIRIS and FGS have completely distinct functions. The former is a scientific tool, and the latter is a component of the telescope's support system. Lastly, we have the Near-Infrared Spectrograph, NIRSpec. It was a contribution of the European Space Agency. Specifically, it was built in Noordwijk, Netherlands. The objective of the instrument was to provide spectroscopy. To do so, 3 observing modes are available on the NIRSpec. An R1000 multi-object mode, an R2700 integral field unit or long-slit spectroscopy mode, and a low-resolution mode using a prism. Thus, the telescope is able to adjust to different modes to capture images at various wavelengths because of this instrument. The James Webb Telescope is nothing short of a scientific wonder and a product of scientific ingenuity. Obviously, we have to wait to receive images and evidence to support man's theory of how the universe began. Till then, I say, keep exploring, James Webb.